Hello students, welcome back to JCE Connect e-learning platform. We'll continue where we have stopped in the previous class. We are discussing about basic electronics 18ELN24 Module 3 operational amplifier and its applications. So far in this module we have discussed about what is operational amplifier, why it is called as operational amplifier, what is the circuit symbol of the operational amplifier, what is the equivalent circuit of the operational amplifier. We have seen what are the characteristics of the operational amplifier, various parameters of the operational amplifier, and also we have discussed about the open loop and closed loop configurations of the op amp. So we'll just have a quick review of what we have studied so far. So ideal characteristics of the op amp. The first important characteristics of the op amp is infinite open loop gain. Then it has infinite input impedance so that it will not allow any current to flow into it. Zero offset voltage, that is both the output offset voltage and input offset voltage should be zero for an ideal op amp. Infinite output voltage range, obviously as infinite open loop gain, so the output also will be infinite. The bandwidth of the op amp should be infinite. Important parameter of the op amp, slew rate, the maximum rate of change of output voltage with respect to time, also should be infinite. The output impedance of the op amp should be zero. There should not be an effect of noise and temperature. Zero offset and bias current. Infinite common mode rejection ratio. As you all know, common mode rejection ratio is the ratio of open differential gain to the common mode gain of the op amp. So common mode gain of the op amp should be zero, hence the CMRR for the op amp should be infinite. Then one more important parameter of the op amp is zero power supply rejection ratio. That is, it is the ratio of change in the offset voltage with respect to supply voltage. So even if you change the supply voltage, the output offset voltage should not change. So the op amp should have zero supply voltage rejection ratio. So here all students should remember that in some of the book it is mentioned that the power supply rejection ratio also should be infinite. It is wrong. The power supply rejection ratio for the op amp should be zero only. And lastly, the op amp should have infinite bandwidth. Next, we also discussed about the two closed loop configurations of the op amp. Those are called as inverting op amp and non-inverting op amp. Now you can see the circuit of inverting op amp. This is called as inverting op amp because here the input is applied to the inverting input terminal of the op amp and non-inverting input terminal is grounded. In this circuit, we have used two resistors. Resistor R1 is called as an input resistor connected in the inverting input terminal, and the resistor RF is called as a feedback resistor because it is connected between the inverting input terminal and the output terminal. Since the feedback is connected in the inverting input terminal, the circuit is said to have negative feedback. And in particular, this closed loop configuration of the op amp is called as inverting op amp configuration. And already we have shown that the output voltage or output expression for the inverting op amp circuit is given by V0 is equal to minus Rf by R1 into Vi. Here the minus sign indicates it is an inverting op amp circuit wherein the output is 180 degree phase shifted with respect to input. Hence the closed loop gain of the inverting op amp circuit is minus Rf by R1, which is definitely very less, and it entirely depends on the feedback resistance Rf and the input resistance R1. So by selecting proper values for Rf and R1, we can design op amp for any gain. The next input configuration or next op amp configuration is called as non-inverting op amp circuit. If you see this circuit and the previous circuit, the only difference between the two circuits is the input voltage and the ground which was connected at the input inverting and non-inverting input terminals are exchanged. You can see here input Vi is connected to the non-inverting input terminal and the inverting terminal is connected to ground through the resistance R1. One important thing that you should remember here is the resistance R1 and RF are untouched or unchanged. They are in the same place for both the inverting op amp circuit as well as the non-inverting op amp circuit. So only difference, as I already told, the input which was connected to R1 and to inverting input terminal is now connected to non-inverting terminal of the op amp as shown here. And already for this circuit also we have derived the output equation as V0 is equal to 1 plus Rf by R1 times Vi. Hence the closed loop gain for non-inverting op amp circuit is 1 plus Rf by R1, which indicates the gain is positive, so there is no phase difference between input and output, hence the name non-inverting op amp circuit. So one more important thing you can observe from the gain here is the minimum gain that we can get from the non-inverting op amp circuit is 1. When you make the ratio Rf by R1 equal to 0, the minimum gain that we can get is 1. So we can't have a gain less than 1 in case of non-inverting op amp circuit. So at the minimum, the gain that we can get from non-inverting op amp circuit is 1. In that case, that non-inverting op amp with gain 1 is called as voltage follower or a buffer, which we'll be studying further in the applications of the op amp. So after knowing the two important closed loop configurations of the op amp, that is inverting op amp circuit and non-inverting op amp circuit, now next important part in this module we are going to discuss is about applications of op amp. So various applications of op amp we are going to discuss here. As you all know, op amp is nothing but operational amplifier. Why op amp is called as operational amplifier? Because it can be used to perform mathematical operations like addition, subtraction, differentiation, integration, etc. Hence the name operational amplifier. So in this section we are going to prove how op amp can be used to perform this mathematical operations like differentiation, integration, addition, subtraction. So in this class we'll discuss the two important applications of the op amp, and the remaining applications we'll be discussing in the next class. So the applications of the op amp can be summarized as, or can be listed as, op amp can be used as a differentiator, op amp can be used as an integrator, it can be used as an inverting adder or a summer or a summing amplifier, it can be used as non-inverting adder, it can be used as a subtractor. We can use op amp as a voltage follower wherein output voltage follows the input, and also we can discuss how op amp can be used as current to voltage converter or voltage to current converter. These are the different applications of the op amp that we have to discuss here, and as already told, in this class we will be discussing the first two applications, that is how op amp can be used as a differentiator and how it can be used as a integrator. So we'll start with the first application, differentiator. So you can see this is the circuit diagram of the differentiator. This circuit is exactly similar to the non-inverting op amp circuit which we have seen just now. This is the non-inverting op amp circuit wherein we have resistor R1 and RF. So in this inverting op amp circuit, if you replace the resistance R1 by a capacitor C, we get what is called as differentiator, and this is the circuit diagram of the differentiator. You can see it is exactly similar to inverting op amp circuit. Only difference is we have used this capacitor C in place of resistor R1, and Vin is connected to inverting input terminal, non-inverting input terminal is grounded, and the feedback resistance RF is kept as it is. So the different components used to construct differentiator are, the heart is of course the op amp with dual power supply, plus VCC and minus VCC, or plus VCC and minus VEE. Then the resistance RF, which is connected between inverting input terminal and the output, which is called as a feedback resistance. Then the capacitor C, which is connected between the inverting input terminal and the input, and the external input Vin is connected to the capacitor C. Now when we connect this circuit, we can see there are three different types of currents that we can see here. One is the current I1 that flows through capacitor C, another current IF that flows through resistance RF, and there will be third current which I have not shown here, that is the current that will try to enter into the inverting input terminal of the op amp. So if we call the current through the capacitor C as I1, current through the resistance RF as IF, and the input current that flows into the inverting input terminal as IB, then we can very easily derive the output equation of this circuit, and we can show that the output in this circuit is directly proportional to derivative of the input. Hence, the op amp circuit in which output is directly proportional to derivative of input is called as differentiator. So now we have to show that here the output V0 is proportional to d by dt of Vi. Now in order to derive the output equation for this, we have to use what is called as Kirchhoff's current law at node B. We have shown there are two nodes denoted by voltages VA and VB. So at node B we have to apply the Kirchhoff's current law. And all of you know that Kirchhoff's current law states that algebraic sum of the currents at a node is equal to 0, or current entering the node is equal to current leaving the node. So if you observe the node B, there are totally three currents. As I said, current I1 is entering into the node B, then current IF is leaving the node B, and also the current IB should leave the node B and try to enter into the inverting input terminal of the op amp. So if you try to apply the KCL at node B, we get I1 plus IB equal to IF. That is the equation 1. Since op amp has infinite input impedance, no current can enter into the op amp. Hence, the current IB should be 0. So, if you substitute IB equal to 0 in equation 1, we get I1 equal to IF. We can call this as equation 2. Almost the derivation is same as that of the inverting op amp circuit which we have derived. Almost the same. Equation 1 is same. Equation 2 is same. Now we have to write what is this current I1 and what is this current IF. If you recall, in the inverting op amp circuit, we have written current I1 as the current through resistance R1 and current IF as the current through resistor RF. So here current I1 is the current through the capacitor C, and current IF is as usual current through the resistor RF. So we have to write what is current I1. We know that the current through any capacitor is given by C into dV by dt, where C is the value of the capacitor and V is the voltage across the capacitor. Here the voltage across this capacitor C is what? The input voltage Vi minus the node voltage Vb. The potential difference between the two ends of the capacitor, that is Vi minus Vb, is the voltage across the capacitor C. Hence we can write current I1 as C into d by dt of Vi minus Vb. We can call this as equation A. Similarly, the current IF is the current through the resistor, and we know that current through the resistor is what? V by R. So what is V here? Voltage across RF. What is voltage across RF? The potential difference between the two ends. One end is connected to VB, another is connected to V0. So what is the potential difference then? It is VB minus V0. Hence the current IF is given by VB minus V0 by RF. We can call that as equation B. Now if you substitute these two currents, that is I1 and IF, in equation 2, we get, you can see here on the screen, C into d by dt of Vi minus Vb equal to Vb minus V0 by RF. That is equation 3. Now we have to simplify this equation 3 and we have to get what is the output equation V0 in terms of Vi. But here in this equation 3 we have Vb, the node potential of node B. Now how to get this node potential of node B? That's where the important concept in op amp called virtual ground concept comes into picture. What virtual ground concept says? The potential at the two input terminals of the op amp should be 0, or there should exist a virtual short between the two input terminals of the op amp. Hence, according to virtual ground concept, VA should be equal to VB. And now if you see this circuit, VA, that is the non-inverting input terminal, is connected to ground. So obviously the value of VA is 0. And according to the virtual ground concept, since VA should be equal to VB, this indicates that VB also should be 0. Right? So substituting the value of VB in equation 3, we get C into d by dt of Vi minus 0 is equal to 0 minus V0 by Rf. So how we got this equation? Just by substituting Vb equal to 0 in equation 3. Now rearrange the term in this equation. You get minus V0 by Rf equal to C into d by dt of Vin, or V0 is equal to minus Rf into C into d by dt of Vi. Right? So here Rf is constant, C is constant, hence the product of Rf and C is called as time constant of the differentiator, and the negative sign indicates it is an inverting op amp configuration. Hence V0 is directly proportional to d by dt of Vi, that is derivative of input. Therefore the circuit is called as differentiator. Dear students, the differentiator is a circuit in which output is proportional to derivative of the input, and from the above output equation we have proved that the output is directly proportional to derivative of input. Hence the circuit is called as differentiator. I hope all of you have understood this. Just a quick review how we can do the derivation. You have to apply KCL at node B. You will get I1 plus IB equal to IF. Op amp has infinite input impedance, no current enters, so I1 equal to IF. Write I1, the current through the capacitor, which is given by C into d by dt of Vi minus Vb, and write IF, which is the current through the resistor Rf, which is given by Vb minus V0 by Rf. So if you substitute these two current in the equation 2 and simplify, we get the output equation, and we can show that it is proportional to derivative of the input. And we have arrived at this output equation by using a very important concept in the op amp called virtual ground concept. That is differentiator for you. Right? Now the next application of the op amp we'll be discussing is op amp integrator. Now there is no much difference between the differentiator in the integrator circuit wise, but definitely the operation done by differentiator is totally different than that of integrator. Now how to get the integrator? So integrator circuit is obtained from the basic inverting amplifier circuit by replacing resistance Rf by capacitor C. How we have got differentiator? Differentiator is obtained by replacing resistor R1 by C, whereas integrator is obtained by replacing resistor Rf by C and keeping R1 as it is. Or integrator can be obtained from differentiator by exchanging resistance and capacitance. So here in the integrator we use capacitor C in the feedback path, resistance R1 in the input path, and we have given input Vi to the inverting input terminal, and we have to show that the output is proportional to integration of the input. Then we can say that the circuit is acting as a integrator, because op amp integrator is defined as the circuit in which output is proportional to integration of the input. Now how we can derive the output equation? Exactly in the same way how we have derived equation for differentiator, we have to derive here. right? Quickly you can derive it. The procedure again remains same. Apply KCL at node B, write the current equation. Op amp doesn't carry any current, so IB 0, you get again I1 equal to IF. Right? What is I1? What is IF? Here I1 is current through the resistance R1, IF is current through the capacitor C. That is the only difference. The currents are exchanged here. In integrator, differentiator, I1 was capacitor current and IF was resistor current, whereas in the integrator, I1 is the current through resistance R1 and IF is the current through capacitor C. So exactly in the same way, we'll try to apply the KCL and proceed further, use virtual ground concept, and we'll show that the output is proportional to integration of the input. So start with applying KCL at node B again. When we apply KCL at node B, we get I1 plus I1 plus IB equal to IF. That is our equation 1. But again, op amp doesn't carry any current because of its very high input impedance. Ideally, op amp has infinite input impedance, so current IB is 0. So we can write equation 2 as I1 equal to IF. Now from the circuit diagram, you write what is I1 and IF. What is I1? Current through resistance R1. So what is it? So I1 will be V in minus VB by R1. And what is IF? IF is a current through capacitor, C dV by dt. So C into d by dt of VB minus V0. Now substitute these two currents, I1 and IF, in equation 2. You get equation 3 as Vi minus Vb by R1 is equal to C into d by dt of Vb minus V0. That is equation 3. Now to proceed further, you have to bring the virtual ground concept in picture. According to the virtual ground concept, potential difference between the two input terminals of the op amp should be 0, or voltage at inverting input terminal should be equal to voltage at not inverting input terminal. So that is VA should be equal to VB. But from the circuit diagram, it is seen that VA is connected to 0, so VB also should be 0. Hence, substituting VB equal to 0 in equation 3, we get Vi by R1 equal to C into d by dt of minus V0. So rearrange the term, you will get minus d by dt of V0 is equal to Vi divided by R1C, or V0 equal to minus 1 by R1C integration 0 to t Vi dt. So from this equation, you can see that again the R1 is constant, C is constant, so the product R1 into C is constant and is called as time constant of the integrator. Therefore, V0 is directly proportional to integration of Vi dt. Hence, the circuit is called as integrator. Again here, the negative sign indicates it is the case of inverting op amp configuration because we have applied input Vi to the inverting input terminal of the op amp. So the output is directly proportional to integration of the input. Hence this circuit is called as integrator. I hope you understood the derivation of integrator. Again I am repeating, there is no difference between the derivation of differentiator and integrator, but I have seen many times students, you will get confused and you will write a derivation of integrator to differentiator and vice versa. So easy way to remember is differentiator, D and C are closer. So in differentiator, C comes first, whereas in integrator, C comes next. If you remember this, very easily you can draw the circuit diagram, and once you draw the circuit diagram, simply by applying KCL and following the procedure, you can arrive at the output equation, and for both the circuit, you can show that output is directly proportional to differentiation of input in case of differentiator, and output is directly proportional to integration of input in case of integrator. With this, we'll close the discussion for